This is the second class of this week. In the first class, we discuss a computer 2D computer code for 2D analysis of truss. Today, we will just demonstrate that code through some examples, and also some of the important thing that we mentioned many times, but we never checked. We also do that exercise during that demonstration. To start with, we will take this example. And then see how to solve it. Okay. So, this is the example we have already. This is the card. This is the code that we discussed in the last class. Now, these are the nodes coordinate. These are the member connectivity, and all these informations are given. We can have this Young's modulus and the area and Young's modulus, and let us solve this. Okay. Now, if we solve it, if we press F5, then it gives you the solution. Okay. So, this is solved. Now we have already done the solution. Let us try to see the solution. Let us first see the global stiffness matrix. The global stiffness matrix was Kg, and this is the global stiffness matrix. If you check, the global stiffness matrix is symmetric, and the size of the global stiffness matrix is 1, 2, 3, 4, 5, 6, 6 by 6. Okay. Now, another important thing, global stiffness matrix, global stiffness matrix is not invertible, it is a singular matrix, because when you take the global stiffness matrix, means it has no information about what constraint you have given to the structure, and that information that will be manifested in some way. And here, if you find the determinant of this stiffness matrix, global stiffness matrix, you check, the determinant of global stiffness matrix is 0. Even if you take the element stiffness matrix, say Ke is the element stiffness matrix, it is the element stiffness matrix for member number 3, and if you take the determinant of this element stiffness matrix, this will also be 0, and which is obvious because it has no information about the constant provided. Now, once you have given the constraint and then partition the matrix like this, if you is K11, then K12, K21 and K22, then this is the partition stiffness matrix. Essentially, this K11, this will be the partition stiffness matrix, and if you take the if you check the what is the determinant of that, whether that matrix is singular or not, let us find out that K11, that is not singular, and which is obvious because K11 is the K11 you obtain is a reduced matrix by substituting the degrees, information about the degrees of freedom in the system. Okay. So, this is consistent with the intuition. Okay. Now, now let us find out the solution. Solution of this is, let us find out what is the force vector. If you substitute u, the total displacement is this. If you recall, if let us plot the deformed shape of this, the deformed shape will be, deformed shape will be this. This will be the deformed shape. Okay, and in this deformed shape, if you so this will be the this was node number 1, this was degrees of freedom. If you recall, this was degrees of freedom 1, 2 and then 3, 4 and then 5 and 6 like this. So, 4, 5, 6 are 0 because this is constraint, and then this u will be the degree, this u will be this is u, okay, and this is your degrees of freedom, this u is this u is the degrees of freedom, okay, and then minus 0.75 is 0.075 is this, and then this value is your this degrees of freedom. So, this is the deformed shape. Now, once we have the deformed shape, we can have we can also see the what is the load vector. If we check F is the first, let us find out support reactions. Support reactions are PU are the support reactions, and these reactions are, we have a load of load of P here, 1 here. So, naturally the reactions will be half here and the reactions will be half here, and the horizontal reaction will be 0. This is a very small value which is 0. So, this is consistent. Now, similarly, we have we can see the what is the force vector, what is the force in different members. The forces are this. So, this force is this is the red one. So, this force is in member, member number 1, member number 2 and member number 3. Here please you have to be consistent with your sign convention, whether we are taking compression as positive or tension as positive. Whatever sign convention we take, depending on that we get the sign convention here. Okay. So, if you change the sign convention, the same value may get this, you will get the same value, but the opposite sign. So, interpretation of this result is very important, that depends on your sign convention. So, this sign convention that we use here is, this is compression, this is compression, this force is compression, this is compression and this is tension, which is very obvious if you look at the deformed shape, which is very obvious because this member, this point is moving from this to this. So, therefore, there will be tension in this member, whereas this member and this member will be in compression. Okay. Now, so let us, so this is the solution of the system. Now, before we move on to another problem, let us do some, let us check some important, you see here Young's modulus was taken as 0.1. Okay. Let us now you calculate the displacement. Let us see the displacement is, this was the displacement at the center, the downward displacement was minus 0.75. Okay. Now, what we do, let us check the Young's modulus. Instead of 0.1, you make it 0.1. Okay. If you make it 0.1, what will happen? If you see the displacement is 7.5. Okay. So, which is obvious. You see, the thing is, what we are discussing is a very obvious thing, but this through the discussion of the obvious thing, through this check, you can check your you can check whether your results, your codes are correct or not. Okay. Now, which is very obvious because it is a linear problem, the force displacement is really linear. So, if you change linearly the Young's modulus, the effect on the displacement will be linear. So, if you increase the Young's modulus, this displacement will be decreased, and if you decrease the Young's modulus, displacement will be increased. And the same thing we have for here as well. If we make it and if we change the change the area to 0, then let us see what happens. This will be your u will be this. Okay. So, it is decreased by 10 times. Okay. So, this was obvious, right. Now, so once this problem is we have solved this, we have the solution of this problem. Next, move on to the next problem, where this also the problem we discussed in when we in some of the classes, and the solution of these problems are also known to us. The solution of this problem is, if you recall, the solution of the problem is, okay, before we have the solution. So, this is the numbering system of this this is the way the degrees of freedoms are numbered, and then this is for different numbers, these are the I and j point and corresponding lambda x, lambda y. We have to just give this information in the code. So, what information we have to give here is this. So, these are the 4 nodes, these are the coordinates of 4 nodes, and the corresponding members of the corresponding member connectivity are this. And let us take Young's modulus and E is 1, and then important is the P1 and P2. If you look at this, your force we have is here. So, P1 and P2, this is the degrees of freedom 1, this is degrees of freedom 2. So, P1 we have 5 and P2 we have minus 10. So, we have P1 is equal to 5 and P2 has minus 10. And then boundary conditions are, if you recall, this is hinge and this is roller support. So, if we see the 7 and 8 are constrained, 5 and 6 are constrained, and then 4 degrees of freedom 4 are constrained. So, only unknown displacements are degrees of freedom 1, degrees of freedom 2 and degrees of freedom 3, and rest all are known displacement field. So, unknown displacement is 1, 2, 3 and list 4, 5, 6, 7, 8 are at the known displacement at the known displacement field, means it is 0 here. So, rest of the thing is again same, and then if you run it and you get a solution like this, Okay. Now, again similarly, if you take the kg, determinant of kg, if you take determinant kg will be 0, which is very small number, is 0. Similarly, if you take the determinant of elements, the member stiffness matrix, say Ke, any Ke, this is the last one, this will also be 0. So, similar exercise you can do. Okay, the forces are displacements are these are the displacements. Please check the displacement. We have the solution, we discussed the solution in one of the classes. You check the solution with these values, and similarly we have the forces, member forces. The member forces are this, and similarly we can check the values of the member forces. Okay. Now, you see, let us do one exercise that let us make the structure. Let us okay. Now, let us okay, just 1 minute. Yes, let us make all degrees of freedom. Let us provide constraint only in 7 and 8, and other degrees of freedom 1, 2, 3, 4, 5, 6. They all are. There is no constraint in other degrees of freedom. So, only hinge we have. Now, the problem is now is this. So, we have just one hinge here, that is it, and there is no other degrees of freedom, right. So, corresponding, if we change in the code, in the input file, this will be the change. Your force will remain same, yes. U known will be only U unknown. U known will be only at the 7 and 8, and all other degrees of freedoms are unknown. Okay, and let us solve. Let us find out the solution. Now, if you see the solution, you see there is an error. Okay. Let us see kg. Kg is absolutely fine. You see, read the error. Okay. There is, see, this same code worked just now, but just we change the boundary conditions, it does not work now. Now, why it does not work? Let us understand that. You probably know that, but still we are emphasizing, in order to emphasize the fact, it is very important. That is what let us discuss that again. The kg is, there is absolutely no problem. It is symmetric. It has been calculated perfectly. Let us see K11, K11, K11 is also fine. Let us find out determinant of K11, kg. Determinant of kg is 0, which was expected. Determinant of K11, is also 0 here. Now, why determinant of K11 is 0? It is very obvious. You look at this structure. If we have a structure truss like this and support only at this point hinge, and then what is the structure stable? This structure is not stable because the number of constraints required to stabilize the structure, we have not provided that many constraints in the structure. That is why the structure is not stable, and this will be manifested. This will be manifested in the solution. When you run this code, you will see that there is something wrong in the structure. So, that is the reason why you could not solve this structure. Now, let us give 1 degrees of freedom. Let us provide one constraint to make the structure stable. Let us make 6 also here. So, 6 you remove and then check whether it is okay or not, then it is fine. Okay. Now, the structure is stable. 3 constraint required, you have provided 3 degrees of 3 constraint, and the structure is stable. Okay. Now, moving on, the last example. This is the solution of this problem that we already discussed. Some of the classes. Okay. Now, let us take this example. This was the solution of this problem, and please check this solution with your. This is the solution. Please you can check the solution. Okay. Now, let us take this example. This relatively complex example, complex in the sense here the number of members and the orientation of members and the number of degrees of freedom is relatively larger as compared to the previous two examples. Okay. Now, all the dimensions and the load is given here. You can prepare the input. Prepare the input means what is the input, what is the nodal coordinates and what is the member connectivity, and I have done it for you. This is this one. So, these are the different nodes and the corresponding member connectivity, and then we have this is degrees of freedom 3, 5 and 7, and this is degrees of freedom 3, 5 and 7. We have these forces, and then these are the known displacement and this is the unknown displacement. Known displacement here only this and this means 4 known displacement. This is also a hinge support. This is also a hinge support. This is also hinge support, otherwise you will see it is not stable structure. Now, it is also hinge support. So, we have 4 constraint. So, these are the 4 constant corresponding degrees of freedom and the corresponding degrees of freedom for which displacements are not known, and then rest of the thing is same, and then if we solve it, this will be the solution. This will be the this is how the structure deform, and if we get these will be the different displacement at different nodes. You can see the displacements are very large. That is because of we have taken a very random arbitrary value of AE, and these are the member forces. These are the member forces, and these are the okay. So, what you have to do is, now if you take any structural analysis book, there are either structural and basic, the first level structural analysis book or matrix method of structural analysis book. There are many examples given in the book. You take every example, each one, and create the input. The solutions are given in the for some of the example solutions are given, exercise problem solutions are given in the book. You take those examples, prepare the input, means what is the node number, what is the connectivity and so on, and then you solve it and then compare this solution with the solution that you obtained from structural analysis 1 or method of section, method of joints, whatever methods we know for solving truss, and then you compare this. Now, you see the same thing if we have a truss which has say 500 members, just an arbitrary number I am giving, we have 500 members, and the same 500, you just create the input file and then just a mouse click we can get the results, we can get the displacements, we can get the forces, we can get all the information that we need about the structure. Okay. And that is the beauty of this method. This method can be translated into a computer code very easily. Okay. So, next class we do the similar exercise for beams, and again get the and try to solve some beams, and then in the subsequent classes we will have the similar exercise for frames. Okay, then I stop here today. See you in the next class. Thank you.